Hello, everybody. Today we're going to continue along with partial fraction decompositions. We're going to take a look at some of basically a more advanced type of problem. I know we talked kind of about yesterday what I would consider a medium difficulty problem. Let me share my screen. So here we talked about what to do basically when we had repeated roots. So like normally this is the general process, and we typically don't do step 0 and 3, but yesterday, like, just those don't come up a lot, but sometimes they do. So yesterday, I showed a specific example where step 3 comes up, basically when we have to deal with the repeated roots, and we kind of showed how to actually use step 3. Today, what we're going to do is talk about one that involves step 0. So let me grab the problem real quick, just a second. Yeah, sorry, just a minute here. So yeah, basically what we're going to do, because when you're dealing with those situations, when you're dealing with situations where where you have to do long division beforehand, it can unfortunately take a long time. So like you could argue that the polynomial long division is almost as much, or it takes almost as much time as it does to uh to do the um actual partial fraction decomposition itself. So here, let me open this real quick. So yeah, so partial fraction, and then let me see if I can find a good problem. If you have any other specific questions, by the way, feel free to just drop them in the chat, or post them in Skool, and then we can kind of talk about them. But here, I'll just go over this problem specifically. So this problem for today, let me pop it in here, is that we want to evaluate this integral. And I've already kind of mentioned we're going to use partial fraction decomposition, right? And we're going to specifically, you might have already noticed, and I've said it before, we're going to use step 0 here. So if we're trying to find, and I'm going to convert it to x, so you remember wx doesn't really matter what you call it. So, or what you call the variable. Like you could solve it with x if you wanted, and then just switch x's to w's at the end. That'll be x cubed plus 9x, and then dx. So basically, if we're trying to evaluate this integral, how would we do it? We'd basically follow these steps. And again, the thing I want to illustrate this time is how we use partial fraction decomposition. Now here, hopefully it's clear that the degree of the numerator is greater than or equal to the degree of the denominator. So 4 is greater than 3, for example. And by the way, just I know it says this here already, but even if this was 3, you would still have to do partial fraction, or sorry, you would still have to do polynomial long division before doing your partial fraction decomposition. But given that it's like this, then how could we do that? Basically, we need to walk through walk through polynomial long division. So how do we do that? First off, the numerator becomes the dividend, and you should write it in descending order as well. And then the denominator becomes the divisor, the thing we're dividing by. And then one tip I'll give for polynomial long division is digits become terms. And yeah, it might not make sense yet, but this is what I explain to all my students when we're doing polynomial long division. Digits become terms. What do I mean by that? The good news with polynomial long division is it almost feels exactly the same as what you did in grade school when you were dividing regular numbers. So let me give an example of that. Let's say we have, like, I don't know, 116 divided by 7. I'm just kind of making that up. But think about how do you actually do this process? Well, the first thing you do is you take the divisor, or sorry, you take the first digit of the dividend, and then you divide it by the divisor. So how many times does 7 go into 1? So 1 divided by 7 would be 0. 0 as a whole number. You can obviously have a fraction left, but we're ignoring that for this scenario. So here, the first one doesn't really matter, but then that's where you kind of pull off the next digit. So how many times does 7 go into 11? 1. Well, we can ask a similar question. How many times does x cubed go into x to the 4th? The way you figure that out is you basically just divide them, right? Like 11 divided by 7 is 1, and then it has a remainder, which we'll talk about. But the bottom line is, like, x to the 4th good, like divided by x cubed, what is that? Well, that's x. So like the x on top here, the x in the quotient is kind of like the 1 is, I guess is my point. So that's the first point. And then think about it. What's the next step you do? Like this is what I want to illustrate. Digits become terms. It's literally the exact same steps if you look at digits as terms. That's the key point with polynomial long division. So what do you do next? Well, the next thing you do technically is you multiply 1 by 7. Like whatever you just got in the quotient, you multiply that by the divisor, and then you write that underneath. So I'm just going to write 7. Similarly, we take x and we multiply that by this. What would we get? We would get x cubed. X cubed plus, or sorry, x to the fourth. I mean, if we multiply that by x, right? Just take this whole thing, multiply by x to the fourth plus 9x squared. So plus 9x squared, right? So the x fourth plus 9x squared is like the logically equivalent to the 7 here. It's just take the quotient, multiply by the divisor. It's a polynomial, obviously. It's not a number, so it's more complicated, but there's an analogy between everything you already know how to do. That's kind of my point. And then what do? Well, we subtract. So what do we do here? We subtract this whole thing, which would really be the same as just flipping the positive signs to negative signs and vice versa. So that's kind of how I think about it here. So just instead of plus plus, it's minus minus. Cool. And then you actually do the subtraction. 11 minus 7 is 4, right? 11 minus 7 is 4. And by the way, there's one other thing that's kind of useful to think about when you're doing these, is that it's kind of useful to line up the decimal place or line up the degrees. So here you could say x to the fourth, and then you could just go straight to like plus 2 like I did. It's actually better to leave a little space for the x to the third power, and leave a little space for the x to the second, and leave a little space for the x to the third power. Or sorry, x to the first power, and then put the plus 2 right here. So it's good to leave some space. Now here we don't actually need space in here, but normally we will, right? Because like I'm imagining this is like the x cubed. So think about it like this. Think about it like it's plus 0 x cubed. That's a good way to think about it, because that's kind of how it is. Plus 0 x squared plus 0 x, and then that can help you line up the like terms better. The key point, or one key point, is that the like term, in order to actually subtract, like you can't do 2 minus 9, for example. Those are not like terms. You can only do like terms if they're in the same like column. That would be like 106 basically, rather than 100, like 116, and then like 0 minus 7. Like you could do it then. That's kind of like what we're doing like this. But the point is, you need to line them up. So here, in order to actually do the subtraction down, that's one key detail to watch out for. That's happens only because this is more complicated. But you should always get, if you did the previous steps correctly, you should always get like 0 here. You should always get 0 in the first decimal place, just like you should always get 0 in the first term. Not digit, but term. And then, 0, you could write 0 here as well, but you don't really need to. You don't really need to write the leading zeros. It's implied. And then here, 0 minus 9, well, that would just be negative 9x squared, right? So the negative 9x squared is equivalent to the 4. That's basically the remainder you get, more or less, when you do that. And then what happens? Well, you pull down the 6. And then here, well, what happens? You pull down the plus 2, and you do it again. So here, like practically over on this side, we would do another round of it, but it's those steps, and you just do those on repeat. So now it's like, how many times does 7 go into 46? Well, 6 times. And then minus 42, we get 4. So like your remainder would be 4 here. And then think about it. Once you get over here, like let's say you actually get to the remainder, like here we're actually already at the remainder, as weird as this looks. Like this right here is the remainder. How do we know it's the remainder? Because the degree of the leading term is less than the degree of the divisor. And that's actually how you know that you've gotten low enough to have the remainder. Like you can't go any more, right? Because x cubed does not go into x squared anymore. X squared is less than that. If this was like x cubed, well, then it would go in negative 9 times, right? Negative 9x cubed divided by x cubed is negative 9. But because this is a lesser degree, we would get like an x in the denominator. So it's like you can't actually divide it in anymore. That's how you know this whole thing is the remainder. Just like here, 4 would be the remainder. So hopefully that logic makes sense. Now, what do we actually do with it? Well, if you think about it, what did we really start with, like on the right hand side? Again, there's an analogy for everything, which is why it's important to see kind of what we're doing here. But basically, long story short, on the right hand side, 116 divided by 7 is equal to the quotient, which is 16, and then you could say four is the remainder, so like 4/7. Or if you wanted to space it out, you could say plus 4/7. That would technically work too. That's like another way of writing what's called a mixed number. You probably learned in grade school, right? So 116 divided by 7 equals 16 plus 4/7. And obviously we can check that, right? So we don't really need to check it, but 116 over 7. And then that should be 6. So we definitely get the 16 in the front, right? And then apparently what we're claiming is 4/7. And that's the 0.57. And you can see that if I did 16 plus 4/7, yeah, that's correct. That is 116 over 7. So that's what we're seeing here. It's the same exact thing. Think about what we did. Like, just to put the terminology on it, what did we do? We said that the dividend, the thing we're dividing, so this is the dividend. So the dividend, it's always the starting numerator, and it's always right there, divided by the divisor, which is right there, is equal to the quotient. Again, you don't need this terminology, but you do need to understand the pattern here. The quotient, which is right there, plus what? What's the color? I haven't used it. Plus the remainder, which is right there, over the divisor, which we already have. That's the pattern. That's what we're kind of proving logically. It's like in this case, 7 goes into 116 16 full times, and then you have 4 left over. So that you can't really do anything. So you just take that 4 and divide by 7. There's a perfect analogy on the left-hand side. It's the initial thing we started with, the dividend, x to the 4th plus 2, divided by the divisor, x cubed plus 9x. It's just more complicated, but everything's the exact same is my point. When you look at, again, digits become terms. So instead of digits, like they're terms in a polynomial. So here, what does that equal? It equals the quotient, which we said is x, plus the remainder, which we said is negative 9x squared plus 2, divided by the divisor, which is x cubed plus 9x. X cubed plus 9x. So let's see if this is true. So if I go to like x to the 4th, so if I have like x to the 4th plus 2, we said, divided by x cubed plus 9x, this is what we're talking about. And what I'm claiming is that that's equal to x plus negative 9x squared plus, what did I say? 2? Yeah, plus 2. Plus 2 over x cubed plus 9x. Voila. Hopefully you can see that. Like, if I color code it better, maybe. Or hold on a second. That should not be there. There you go. So here, the two curves are literally on top of each other. They're the same curve. That's the point. So yeah, it really is true what we said here, right? It really is true what we're saying here. And remember, what are we doing? We're basically trying to find the integral of this, right? We're trying to, our original goal was to integrate this thing. I just switched the x fourth plus 2 around slightly. But basically we're trying to solve this. So how do we solve that? We take the integral, of both sides. So instead of taking the integral of the left side, that would be equivalent to taking the integral of the right side. And now how do we take the, so that's step 0. We just did the polynomial long division, and now we can continue with the problem. Now here, there's kind of, I guess, depending on that, there's kind of another step too, because here, this is actually easy to integrate. Like we can do this in one line. This is hard. And we're going to need partial fraction. Now that we've forced, like with polynomial long division, we can force the degree of the numerator to be less than the degree of the denominator. Now we can actually use partial fraction decomposition with that, which is like a leftover rational function. But here, just to get started, that's actually easy. We can do that, no problem, right? So if I integrate that, so plus the integral of negative 9x squared plus 2 all over x cubed plus 9x. This is easy. We already know that's 1/2 x squared by your anti-power rule, right? And now the real problem is, like, the real work comes in where we try to find this. So this is like the real work now, right? So that, hopefully that makes sense. But now this is the real work, and we would do that with partial fraction decomposition. So hopefully that makes sense. Now, how do we actually do it? Now it becomes a normal partial fraction decomposition problem for the remainder. It's for the remaining part, or the remainder, basically, the remainder over the divisor, technically. So now, again, normal problem for partial fraction decomposition. We've already gone over this a lot, but hopefully this is all kind of review. So from here, it's normal. From here, all the things you're used to based on the last couple of days that we've been talking about, that's normal. So we've done step 0 to force the degree of the numerator to be less than the degree of the denominator. Now step 1 is we factor, right? So factor the denominator, negative x squared plus 2 over x times x squared plus 9, right? And then, so we factor the denominator. The factors in the denominator on the left become denominators in terms on the right. So this is going to be divided by x plus, and this is going to be divided by x squared plus 9. If this was x squared minus 9, by the way, we would be able to factor this further, right, into x minus 3 times x plus 3, right? Difference of squares. But because it's x squared plus 9, you actually can't factor this anymore, right? Which is not ideal, but sometimes it happens. This is what we call an irreducible quadratic. Irreducible, I won't spell that. Irreducible quadratic. It's a quadratic because it has an x squared, and we can't reduce it anymore because we can't factor it anymore. Again, ideally, we like to have no x squares left, just like x minus something, x minus something, x minus something, and all those multiplied. That's like when we've completely factored it. But here we can't do that practically. Now, to be clear, according to I don't want to get too deep down the rabbit hole of algebra here because there's actually some pretty deep algebra, much deeper than you might think. But there's a theorem in algebra which says that for any quadratic, there are going to be two, what are called zeros. There are going to be two factors or two zeros. So the problem is what's really going on is they're complex factors. So x plus 3i and then x minus 3i. That's what it really is. If you FOIL these out, you'll get, this is a difference of squares. You'll get x squared minus 9i. Or minus 9i squared. What's I squared? -1. So minus 9 times -1, positive 9. So there are two factors, technically, by the fundamental theorem of algebra. It's just that they're not real numbers. They're complex numbers. That's kind of the problem. So that's why I say that. So there are technically there are zeros, but there are no real there are no real zeros, which is why we can't reduce it anymore while keeping them real numbers. Hopefully that makes sense. But basically, for the purposes of partial fraction decomposition, we should pretend like complex numbers don't exist. Pretend like imaginary numbers don't exist. It's kind of weird in math. Like sometimes you pretend like they do exist, sometimes you pretend like they don't. It's kind of ambiguous. But here in calculus, generally, at least in like calculus A, B, B, C, we pretend like they don't exist, right? So that's why, for that reason, we can't reduce them anymore. But that's not a problem. We know how to deal with them, or we'll see how to deal with them. Step 3 is not applicable, right? So, and I want to be 100% clear. This, just because this is a quadratic, does not mean it's a repeated root. It's only a repeated root if you square on the outside, right? So if you have x, you can have whatever you want inside the parentheses, but it's only a repeated root if you had like a 2 or a 3 out there. If you can't simplify this term anymore, it's not a repeated root. So that's a little bit of a nuance, but hopefully that makes sense. And then now, the numerator for each term on the right is a polynomial 1 degree less than the denominator. How does that work? Well, what's the degree of this polynomial? Technically 1. It's like you can imagine as x to the 1 plus 0. The degree is 1. Well, what's 1 less than 1? 0. So we need a 0th degree polynomial right here. What would that be? Just a constant. And we'll just call it a because we don't know what the constant will be yet. But a is kind of a placeholder. A is a variable. Remember, we go to the beginning of the alphabet to get a bunch of new unknowns, essentially, for the coefficients. Cool? And this one, what's this? A 2nd degree polynomial. So previously, we haven't really dealt with this before. Everything we've dealt with is like a 1st degree polynomial, and we know that would be like bx, or that'd be basically b, right? This is the first time we're dealing with a 2nd degree polynomial in the denominator. That's not because it's a repeated root. Remember, that doesn't count. So here, what would be, so the degree of this is 1, right? Well, what's 1 less than 1? Or sorry, the degree of this is 2. What's 1 less than 2? 1. So we need a 1st degree polynomial here. In other words, like mx plus b, or I'll write bx plus c. Because we just remember, we go to the beginning of the alphabet to grab more unknowns. So hopefully that makes sense. So that's step 4. Now we've successfully set up the partial fraction decomposition here. And then from here, it's kind of a normal process, right? We need the common denominators. We kind of already know how to do all this, right? So on the right-hand side, to get that common denominator, so x times x squared plus 9, what do we need? We need the a times, so we need the a times x squared plus 9 plus bx plus c times x, right? So hopefully that makes sense. You'd have to do x times x here, and then x squared plus 9 over x squared plus 9 here. That's why this is happening that way. That's good. And then now, again, we can kind of set the numerators equal. The denominators are clearly equal right now. So in order to find an a, b, and c value that make this true, basically the numerators have to be true. So if I pull these down, let me simplify this a bit. So if I just essentially get rid of the denominators. So let me see if I can do that more efficiently. There you go. And then here, so there. So we need these to be equal. So how do we do that? This is where things get a little bit trickier, right? So the old way of doing it, what was the old way? Remember, the old way was basically choosing an x value that would cleverly make certain variables cancel out. So we can still do that, to be clear, right? So it's like we can't really. I'll say this: we can't really make a disappear because there's actually no way to make this thing 0 if you think about it, right? If you try a positive number, doesn't work. This whole thing's positive. Try 0 squared plus 9, also positive. If you try a negative number like -1, that would also be positive. Like because of the square, basically. If we had that, we could just make it -9. But because of the square, there's actually no way we can make this whole thing 0. We can't make that go away. But we can make this go away with one clever substitution. Hopefully that's clear. X equals 0. So let's give that a try, see what happens. We get -9 times 0 squared. So that's going to be just 2 on the left. And then we get a times 9. So I'll just say 9a, right? Because that's 0. And then this whole thing is going to be zeroed out. So hopefully that's clear. At least we just figured out that a is equal to 2/9. There you go. That's at least some progress. But we're going to run into trouble on the rest of it here. So if you think about it, because again, like I said, there's no way. There's kind of two problems. One is there's no way to make a 0. If there was, we would at least know what bx plus c is, um, or we would know like we have an equation relating them. But there's actually no way to do that. So at this point, we're kind of stuck with the easy way. Remember, what we've been using is kind of the easy way. What we're going to do now, we're kind of forced to use the hard way, if that makes sense. So for the rest of the way, we kind of have to use the hard way, except there's one difference now. Now we've at least figured out what a is, and we know that that's 2/9. Now, to be clear, you could have not done what we just did to like find what a is. You should do that because it gets a lot easier, right? Like here we have 3 unknowns, one, right, a, b, and c. Once we do the hard way, we're actually going to have a 3x3 matrix to solve, like a 3x3 system of equations, if we did it like the hardest way here. So we're going to be forced to do the hard way here, I guess is what I'm saying. In the previous 2 days, we haven't been forced to do that yet with our partial fractions, but you need to know how to handle this because sometimes, practically speaking, sometimes you will be forced to do that. That's kind of what's happening here. Now, in order to deal with this, how should I word this? Just because you can solve just because you can't find all 3 values with the quick technique or the easier technique doesn't mean you shouldn't try to get as many as you can. Every single one that you solve for takes it basically decreases the pain you will feel by a lot. So just for context, if we didn't do what we just did and like set x equal to 0 to cleverly cancel out the thing on the right to find a, if we did not do that, what would have happened? We would have, and you'll see how this is going to happen. The only way to solve this would be the hard way, which is going to involve a 3x3 matrix, basically a 3x3 system of equations. That's annoying. It's annoying to solve three. It's especially annoying to solve 3x3 and above. You can do it, obviously, but it's not fun. Because we just found a value with the clever way, the quick way, and we now know that a is equal to 2, now we don't have 3 unknowns anymore. If you think about it, we only have 2 unknowns, b and c. So now we're going to get a 2x2 system of equations. That is a lot more manageable. It's a lot less painful to solve a 2x2 system of equations, significantly less painful than a 3x3. So just because this won't get the job done entirely, just because we can't use the quick way for everything anymore, doesn't mean it's not valuable still. It is valuable. It makes the hard way a lot less hard if you do this one to get as many as you can. So hopefully that makes sense. Now, here's the hard way. The hard way is you need to combine all the like terms on the right. So how would we do that? First, I would distribute. So I would get, hopefully that makes sense, 2 ninths times x squared plus 2 ninths times 9. The 9s are going to cancel out. I'll just get 2, right, if I distribute that in. And then we need to distribute the x into this thing. So it'll be plus bx squared plus c times x. And then we need to combine like terms. So think about it. What terms have x squared in it? These two. So this is going to be 2 ninths. Think about it. 2 ninths plus b. We still don't know what b is, by the way, times x squared, right? So we've handled those, and I would kind of underline them or cross them out when you after you use them, just so you, because it's not so bad with 4 terms, but imagine we had like 8 or more. That happens sometimes, and it's like you kind of forget. Oh man, did I use that? Did I not use that? It's important to be organized so you don't forget. So that hopefully makes sense. Then the next term we want is x to the first power, or just x. There's only one cx, so plus c times x, and then plus 2 is the only thing left. There's just the constant. So there you go. Now, what's the way to look at this? So we've combined like terms and factored, or not factored. We've simplified on the right, and now on the left, look at it like this. Instead of negative 9x squared plus 2, look at it as plus 0x plus 2. So that's what it is, really, right? Like there, you can imagine there being an x there, but it's just 0. So if you look at this, then this is actually pretty useful, right? Because first off, we see the plus 2, right, as expected, so that's good. And then these have to be the same, right? We have plus something times x, plus something times x. And then we also have plus minus something in this case, but plus something times x squared. So think about it. Basically, like look at the orange. Let's focus on the orange. Like the 2, we don't really learn anything from that. It's just that's what's supposed to happen. But here, in order for these to truly be equal, again, that's what we're trying to find, the b and c values that force these to be equal. Here, well, c has to clearly be 0. So hopefully that makes sense, right? That's the only way to make the right side equal the left side. If it's plus c times x, that's got to be plus 0 times x. C's got to be 0. So we know c is 0. There you go. That was easy, right? So this is actually, I take that back. The way this problem turned out is we did not need to use a system of equations. Technically, this actually is a system of equations, because you're going to say c is equal to 0. And then, so that's that. And then you're going to say, what is this? You're going to say b plus 2 ninths is equal to negative 9. So in other words, b is going to be equal to negative 9 minus 2 ninths, whatever that is. These are technically a system of equations. It's just that they're simplified. What you really got to watch out for, what's really painful, is when if you had like a c here instead of the 2 ninths. If we left this as a, if we didn't already know that a was basically, or what did we say? A was 2 ninths. Yeah, so that would have ended up being a. Then that would be painful, actually, right? Because then we would have what, a plus b equals negative 9, and now we are dealing with a system. You can see how it's kind of coming together. We're now dealing with a system of equations, and the plus c would have also been more complicated as well. So hopefully that makes sense. Like it could have been worse, right? If you don't like the work, I'll just repeat, I sound like a broken record probably, but the work we did here to find a was worth doing, even though it didn't get us all the way there. It made the system of equations so much less painful that it's technically a system, but basically not. So here, what's this going to be? This is going to be negative 81 over 9 minus 2, negative 83 over 9. So hopefully that makes sense, that in order for this to make sense, a has to be 2 ninths, b has to be negative 83 over 9, and then c has to be 0. So that's good. So it actually turned out to be a medium difficulty. So we were able to use the quick way to find one, and it turned out to, it's technically a system of equations when we pattern match, when we combine like terms and then pattern match coefficients on both sides. We technically got a system of equations, but it was an easy system because it was basically already solved for us, right? It was just for each equation, there was only one variable in it. A system of equations when you have multiple variables in each equation, and it's significantly more painful. But this actually didn't turn out that bad. There are other problems where it does turn out to be bad. You might get I'm just making this up, but you might get an equation that looks something like this. And then you have 3 of these basically, and then there you go. That would be like an example of a 3 by 3 system of equations. This is the worst case scenario. This is like the hardest way to solve it. and you basically have to solve a 3x3 system of equations, like using matrix math and whatnot, to find the A, B, and C values. That's the worst thing that can happen on these, but here we avoided it, luckily. But you can always see, like, we did the hard method, it just turned out to not be as hard as it could have been, like with the real deal system of equations. So we kind of lucked out a little bit. That's good. Now, coming back up to this, so let's combine everything we know now. So, and remember, let me pull down the A. We originally found that A is equal to 2/9 before, right? So we know that. And now, if we combine these, so we now know these, and we know that this B. So let's think about this. So now the thing on the left, that's going to be what? That's going to be 2/9 over x plus, and then what's b here? B is negative 83 over 9, so it's going to be negative 83 over 9 times x, and then c0, so we don't need to write plus 0, over x squared plus 9. There you go. So this is a long problem, as you can see, so let's remind ourselves of where we even came from. We started off after the polynomial long division. We finally got to the point. So these are long problems. Yeah, let me make a point of that. You can see how long this problem is, right? It's like ridiculously long. But basically, what we did recently, right? We initially did the polynomial long division to simplify that, and now we got this basically rational function where the degree of the numerator is less than the denominator, so we can actually solve it with partial fraction decomposition, which is what we're doing now. And we just did the partial fraction decomposition, and we figured out how to decompose this fraction into different parts. Now we can kind of replace that, right? So now it's like in here, we basically, like, you could say the integral of this entire thing, like, right, just replace this with that. Or what the immediate next step would be, it would be to just separate them, right, into separate integrals. So that's what I'll do. I'll just jump right to that. So this is what we need to do now. And these are significantly easier to solve. So if you think about it, what's going to happen here? Well, and you always want to factor out the numerator, by the way, like the actual constant values, just to make these a lot easier to integrate. And then here, this will be negative 83 over 9 integral of x over x squared plus 9 dx. This, hopefully, is clear that the antiderivative of 1 over x, we've talked about this before, it's just natural log of x. So that'll be 2/9 natural log of x. Cool. Minus 83 over 9. You can do u sub here. If you're going to do u sub, again, we've talked about the rules and the strategy behind u sub before. But basically, you're going to, like, there is no inner function here, or there's no obvious inner function. So if you set the derivative equal to the denominator, that will work. Or sorry, not the derivative, u equal to the denominator, I mean, the x squared plus 9. That will work. I won't rehash all the u sub stuff that we've been through before. But this is actually simple enough that you can do it in your head if you want. So here, think about it. Well, actually, I take that back. So you can do it in your head, but I will hold off on that. It's probably better for this scenario. Probably better to not do it in your head, I'll say. But you can. So like this one's simple enough that it's reasonable to do. If I say x squared plus 2 du dx is equal to 2x, so dx is equal to du over 2x. So if we actually make the substitution, how's that going to go? It's going to go, we're going to have the x in the numerator. We'll have the u, right, x squared plus 9 in the denominator. And then the dx is going to be du over 2x. All right. And then here you can see the x's cancel. So those go away. So we're going to have a division by 2. So pull that out of the integral. Division by 2, 1 over u du. We can solve that, no problem. That's just natural log. So here, this will be, I guess, negative 83. 83 is not divisible by 2, so we can't really simplify that. So I'll just say over 18. And then this will be natural log of u. What's u? Remember we said x squared plus 1, right? X squared plus 9. X squared plus 9. And then we need the plus c, remember? So there you go. That's that one. That's that one. And you might think that's the answer, but you can't forget the term we got on the outside from the original polynomial long division. So final answer is this whole thing. So this is kind of crazy, as you can see, but it is logical, right? So it's like there is a systematic process to solve this. It's just a long, drawn out, annoying process. That's all. but it is a systematic process at least. So these rules, again, these rules work for every partial fraction decomposition problem in terms of like how to actually do it. Each individual step is not easy, and it's very easy to make a mistake algebraically. But if you don't make a mistake and you just follow these steps, you will set it up correctly. And then from here, we talked about how you'd actually find the correct A and B values and how you could kind of work your way down to the end. So there you go. Hopefully that makes sense. This is not as hard as it can get, but it's close, I'll say. Like the only way it really could have gotten harder is like they could have made finding A, B, and C a lot harder. They could have forced us to use a system of equations, basically, where, like I said, here we were able to kind of sneak our way out of that. We kind of got lucky that this didn't turn out as bad as it could have been. But it, in other problems it might. So yeah, so that makes sense. But other than that, this is a pretty involved problem, as you can see. It's like we ran into a lot of roadblocks with this problem that we have not run into the last couple days. So this is good to see. This is how you do a harder partial fraction decomposition problem. So there you go. Hopefully that all makes sense. If you have any questions, feel free to drop them in the chat or drop them in Skool, and I can respond to them. But yeah, other than that, hope that makes sense to everybody, and I will catch you next time. See you.